Good, thank you. Exciting to start a new week. Okay, so I'm going to be sharing my screen here. Just a moment. Can you guys see the screen with PowerPoint presentation? Hello?
Yes, we can see the presentation.
Okay, yeah, sounds good. Thank you. Okay. So I see that students are still coming into the room. Let's wait a couple of minutes and check port. Yes. Okay. All right. Okay, so what we're going to be doing most of the week is we are going to be reviewing the topic of angular momentum and angular momentum conservation. Now, can you tell me whether you have seen this topic in high school or not?
I haven't seen this in high school, no.
No,
okay, so not. I'm seeing, wow, so many no's. Okay, all right. So for those of you who have seen the topic, can you tell me whether you're Canadian students or whether you're international students?
I went to high school in the US.
Okay. So some of the Canadian system is actually teaching this, while most of it's not. Okay, I'm gathering this information because it turns out that there are certain topics that were not covered in high school, and I'm trying to figure out whether they're covered mostly for international students and less in Canada, or whether there is any kind of distribution. I might be able to prepare a survey for after the finals are over, over the Christmas break, and I would appreciate if you guys actually fill out that survey. It's going to help me to figure out what I can do in the beginning of the course for next year in terms of preparing the students for the course. Okay, all right, sounds good. So nothing scary. This is actually a pretty intuitive topic. The definition of angular momentum is relatively straightforward, but if you find out that I'm going too fast with the definitions and the descriptions, let me know and I'll try to slow down. We do have plenty of time between today's and tomorrow's lecture to spend on the topic. Slow me down if you think that I'm going too fast. Okay. So we have, my computer is asleep right now. It doesn't want to work. Okay. There we go. So before the midterm, actually immediately after the midterm, we have defined a parameter in physics, which we called a linear momentum. So at that time, we said that whenever we have a massive particle with mass different than 0, as long as that particle has a non-zero linear velocity v, then what we can do is we can define a parameter which we call the linear momentum, which was a vector equal to the product of the scalar quantity, the mass, and the vector quantity, the linear velocity of the particle. Now, the orientation of the linear momentum was determined by the orientation of the linear velocity vector, so in the same direction as the linear velocity. Now, in the rotational world, we can define a very similar parameter, but we have to account for the fact that in this case, the particle is not going to zap on a straight line, is actually going to rotate either on a circular trajectory or a partially circular trajectory, right? So in that particular occasion, what we can do is we can define a new parameter called an angular momentum. That one is labeled with a capital letter L, and can be expressed as the product of the moment of inertia of the particle relative to a chosen axis of rotation times the instantaneous angular velocity of the particle. So if we were to focus on the red equation here and we compare it to the black equation that defines the linear momentum, we see that there is a great similarity between those two equations, right? So instead of linear momentum right now, we have an angular momentum, which is a vector. Instead of mass, which is a scalar parameter, we actually have a moment of inertia, which we can consider a scalar parameter for the discussion that we have in this course, right? And then instead of linear velocity here, we're actually going to have an angular velocity in the rotational world. Now, what can you tell me about the direction of the angular momentum vector? Is it in the plane of the rotation or is it outside the plane of the rotation?
It's perpendicular to the plane.
Is perpendicular to the plane of rotation. That's great. And what about the direction relative to omega? Is it in the same direction or in opposite direction to omega?
It follows the right-hand rule.
Bro, there's one super try hard one.
Or no, it's,
Okay.
yeah, it's just,
So that was a little bit the roundabout answers that I've heard. Can the moment of inertia be negative?
No.
No, the moment of inertia is always a positive property, right? So we generate the vector for the angular momentum capital L by multiplying the vector of omega by a positive number, right? So that means that the direction of the angular momentum is always going to be in the same direction as the instantaneous angular velocity omega, right? Do you guys agree with me?
Yep.
Okay, so again, if you have an object that is spinning around, as my fingers of my right hand are showing, then my thumb is going to be showing the angular velocity vector sticking out of the plate of rotation. And then the angular momentum for that object is going to be a vector, again, in the same direction as the thumb is pointing. Now, in terms of unit vector, sorry, in terms of units, the angular momentum is going to be measured as, okay, so I didn't get to the units yet. A little bit of diagrams. On the diagrams here, I'm showing a solid object, which is the disk. When the disk is rotating in the counterclock direction, both the angular momentum vector, the green arrow, and the instantaneous omega, red arrow, are going to point in the same direction, or we're using the right hand. Now, the units for the angular momentum are kilogram times meter squared, then divided by seconds, right? Because we know that the moment of inertia is actually going to be kilogram. Did I actually, is that correct? It is correct, yes? Because omega is going to be 1 radians over second, but the radians actually can be skipped and we can actually use 1 over second. Okay, so let's think about it if there is another way to actually define the angular momentum for a moving particle. And if there is a way to connect the angular momentum L vector with the linear momentum of the particle P, as it's defined here in this relationship. So if we were to consider a particle going on a circular motion, and for the sake of the argument here, we can say that this is a uniform circular motion, then the angular velocity of that particle is going to stay constant over time. And what can you tell me about the linear velocity of the particle, the tangential one? Sorry, say this again. It's going to have the same magnitude. So Abdullah, you're absolutely correct. What about the direction?
It's constantly changing because it's a circular motion.
Exactly, it's going to be changing constantly, right? So now what we can say is that we are going to have the linear momentum vector for the particle, P, that is going to be pointing in the same direction as the linear velocity V. So that vector also is going to have a constant magnitude because the mass of the particle doesn't change. It doesn't break down. It doesn't gain any weight, right? And then the magnitude of V is going to stay constant. Okay, now what we can do is we can actually define the angular momentum as a product of I omega. But when we can look at the particle, a point mass here, we know that the point mass that is spinning around on a circle, a distance 1 radius away from the axis of rotation, then the moment inertia of that point mass can be expressed as mr squared, right? So now what we can do is we can rearrange a little bit this particular equation number 1 by remembering that there is a relationship between the linear tangential velocity V and the angular velocity of the particle through the radius of the circle. So when we do the cross product between r and omega, we're actually going to get the tangential velocity v. So if we were to use equation number 2 and do a substitution for omega in 1, what we are going to get is the following. We can actually come up to the following formula. We are going to have that the angular momentum can be expressed as the mass times the product of r and v. And then because the mass of the particle is constant, we can put it anywhere in the brackets. We can put it in front of the r, or we can choose to put it in front of v. And if we choose the second option here, then we're going to end up with the product of mv. But mv is the definition for linear momentum of the particle. So now we have derived a different expression for the angular momentum that is going to relate the linear momentum of the particle p with the radius of the circular trajectory that the particle is moving on. Now, although for this definition, I used constant motion with a constant omega, we don't actually need that requirement when we derive this formula. We can consider an accelerative or decelerative motion as long as we take one instant in time and we consider an instantaneous omega, then we can actually define the red formula here for the angular momentum as the instantaneous angular momentum for the particle at this particular position. If then the particle speeds up, then that angular momentum is going to grow in magnitude over time. Okay, do you guys have any questions about how we derived the formula? Anything that is
Professor,
yes?
when you're starting with angular momentum, you have mr squared omega, and then when you sub in the linear velocity, I'm kind of confused like where the other r goes in r squared, because you only have r cross v.
So from equation number 2, you're going to get v over r. Yes, and here in formula 1 you have r squared. So when you do the substitution, you're going to have m r squared v over r. Yes, so one of the r's is going to cross out.
Okay, I see.
Do you see that?
Yeah, thanks.
Okay, you're very welcome.
Wait, so if you get that omega equals v over r, then how do you sub in r cross v in the next line?
Oh, okay. So then you use your right angle to actually get the direction correctly, right? But for the substitution, you can actually drop the cross product, assume that there is a right angle. Actually, this is given. You don't assume it. It's actually given that's a right angle. So it's going to be just r omega times sine of 90 degrees, which is going to give you a 1. So algebraically, you're going to get that omega is equal to v over r. And then when you're left with only one r here, you know that L sticks out of the plane of rotation while V is in the plane of rotation, and so is P. So in order to get outside of the plane of rotation, it has to be a cross product. Did I answer the question correctly?
Yeah, that's good.
Okay. All right. So now what we're going to do is we're going to use our imagination a little bit. Let's say that we have a little particle here with a mass m, and we choose a coordinate system at point O, where the particle started moving. And then over time, the particle is going to move on a straight line farther and farther and farther away from point O. So for that particle, we can define a linear momentum equal to mv. However, because the particle is moving radially relative to O, we can also define so-called radial angular momentum, which is going to be the cross product of R and P. So essentially, we're going to have an RP sine of 0 degrees, because right now you have the radial vector in the same direction as the P vector, right? So the sine of the angle is going to be 0. And that means, the angle is going to be 0, and then the sine of the angle is going to be 0. So for any particle that is traveling on a radial trajectory relative to origin of coordinate system, we can say that that particle has 1, a linear momentum, and 2, angular momentum that is going to be 0. Now, if the particle is traveling away from point O, we can always put the particle on an imaginary circular trajectory for its position in space here. So if the particle is one small radius away from point O at a time t1, right? Although the particle is traveling on a linear trajectory, we can also imagine that the particle momentarily belongs to a circular trajectory. So for that particular particle, we can also identify an angular momentum that is going to be non-zero, and that's going to be RP sine of the angle 90 degrees, right? So that's going to be directly for RP. And then the particle moves to a new position in space. So relative to that coordinate system, if you imagine the particle moving in a perpendicular direction, right, then we can say that that particle is going to have an angular momentum equal to RP. Does this make sense?
Right. So I guess another way to think of this would be if the object is traveling in a linear fashion, it isn't going to have an angular momentum, or if it's traveling in a angular rate.
It is about the choice of coordinate system. So let's try to work with me. Let's say that the ball here is the particle, right? And my little orange car here is going to be point of the coordinate system, right? If the particle is traveling on a linear trajectory radially relative to point O, the coordinate system, then that particle is going to have a non-zero linear momentum, but it is going to have a 0 angular momentum. However, if the particle is moving toward you, toward the screen of my computer here, I can still pick this point O's origin coordinate system, right? But now, because the radial direction here is perpendicular to the linear velocity and the linear momentum of the particle, now that particle can be thought as if it's momentarily moving on a circular trajectory, and that particle is going to have a non-zero angular momentum L. Yes?
Oh, okay, yeah, that makes sense.
Okay, I'm glad we got it.
So at any moment, oh, sorry.
Excuse me?
Yeah, so yeah, you go first.
No, go ahead.
No, go ahead, you go first.
All right, so at any given moment, the angular momentum changes because the radius is changing with respect to the origin.
Yes. So what's going to happen is that, let's say that the particle, we choose our coordinate system to be the orange car here, right? We fix it and we don't move it. But then we choose the particle to be moving sort of on a diagonal way relative to the radial distance here. So when it moves on a diagonal way, it's going to translate radially, but also is going to have a component in the perpendicular direction to the radial direction. Do you see that? So then you're going to have an angle between 0 and 90 degrees between the radial vector R and the linear momentum vector. So then when you go for a cross product here, you're going to have RP sine of an angle that is going to lie anywhere between 0 and 90 degrees. It's going to be bigger than 0 and it's going to be smaller than 90 degrees, right? And that's going to give you an angular momentum that is going to be smaller than the maximum, but larger than 0.
So in such a motion, it has both linear and angular momentum at the same time.
Yes, exactly.
Thank you.
Right? Does
So
anybody
Professor,
else have? Yeah.
So are you saying that the angular momentum is dependent on a reference point?
Yes, so we can choose a reference point anywhere in space around the particle. Relative to that choice, as long as we don't move that reference point, right, we are going to see the particle moving away. And there are multiple options. If the particle is moving only along a line that is a radial line, then the particle is going to sustain a linear momentum that's going to be non-zero, but its angular momentum is going to be 0. As long as the particle goes outside of that radial line, whether it goes at a small angle, larger angle, 90-degree angle, then that particle is going to have a non-zero linear momentum and a non-zero angular momentum, right? And so for any particle motion, you can always pick somewhere a point in space and say, relative to that point, I can define a non-zero angular momentum, right?
I see. Thank you.
You're welcome.
So if it travels along a line that doesn't go through the origin, it will have angular momentum.
Yes. Only if it travels in a radial line, like it's shown here on the first diagram here on the where my mouse is pointing. Only in that particular case, the angular momentum of choice is going to be zero relative to the chosen point of coordinate system here, right? But if you have any other angle, then it's going to be different. Okay, let's see whether I have a diagram for this one or not, maybe in the next slide. Okay. So I borrowed these diagrams from a textbook because I thought that it might be helpful. If you look at three-dimensional coordinate system here, and we look at the orange particle here, that particle is going to be located one radius away relative to the origin of the coordinate system. Now, if that particle is moving along the green vector for the linear momentum of the particle, and that vector makes an angle phi relative to the radial direction, then the angular momentum of that particle relative to the choice of the coordinate system here is going to be non-zero and is going to have a value of r cross p, right? And as long as that angle phi here is smaller than 90 degrees, then the calculated L here is going to be below the maximum possible value for L, which is going to occur for phi equal to 90 degrees. Does this make sense now?
Yes.
Yes. Okay. So let's consider a scenario. I know that some of you actually have looked into a problem on the assignment that was asking you to calculate something different than the angular momentum, but we can use it as an example here. Let's imagine that this black dot here is a little bug that started moving from the center of the circle here on a disk that is rotating. And now the little bug actually is moving radially like this. What is going to happen to the angular momentum of that part, that little bug?
It grows.
It is going to do what?
It grows.
It grows. Oh, it's going to increase over time, yes? That is correct, because the radial vector is going to increase, and as long as the velocity stays the same in terms of magnitude, right, then the increase in the radial direction is actually going to increase L. If the bug decides to decelerate and slow down at a rate proportional to the increase of R, then we can actually sustain a constant angular momentum. So if you were given a conceptual question on the final exam, worded in a similar way, I might make it a little bit tricky by giving you a general rule rather than a specific case. And you have to figure out whether the L is going to grow, is going to stay constant, or whether it's going to go down over time. So you have to consider that you have two components. R can increase and decrease, but also the velocity of the particle, and therefore the linear momentum can also change over time unless the text of the problem tells you that it's fixed to a constant value. Does this make sense?
Wait, so in that case, if the angle isn't like the, oh wait, I forgot what I was gonna ask, right?
Okay, so what I was saying is if the bug started sprinting from the origin and started slowing down here, you can imagine a rate of velocity, of linear velocity, that is going to be changing at the same rate that you're increasing the radial vector here. Then you can imagine a scenario where the angular momentum is going to stay constant by magnitude. Do you see that? Yes, no, or do you disagree?
Right, yeah.
Okay, makes sense. That's what I wanted to hear. All right, so when we talked about linear momentum, we defined a special condition where we said that whenever we have a system of particles, well, I'll backtrack a little bit. We said that in physics, physicists defined linear momentum to be able to deal with situations where there is collision between two objects, or there is an object that is actually falling apart into different parts, and we want to find out if we know the way the object was moving before it exploded into multiple different parts, or before it collided with another object, can we actually predict what's going to happen to the parts of the system immediately after the collision? Now, in the linear world, we considered collision of two particles, and we talked about that the internal forces during the collision are going to be equal to each other by magnitude in opposite in direction, in accordance with Newton's third law for the linear world, right? And as long as there were no external forces to change the linear momentum of the system, then that linear momentum is going to actually get conserved over time. And the way we derived that formula was to start with the definition of the linear momentum, then do a derivative over time to find out how that linear momentum could be changing over time. And then we defined in broad sense, the linear momentum conservation law that said that the only way that we can change the linear momentum of a system or a particle is to actually apply an external force to that particle or system over a sustained period of time. Right? And if there are no external forces, that the change of the momentum is going to be zero. So that means that the momentum of the system is going to stay conserved over time. And this expression in orange is basically the linear momentum conservation law that we learned a few weeks ago, right? Or what you learned in high school too. Now, in the rotational world, we can imagine a very similar scenario, and we can use pretty much the same approach to define a conservation law for the angular momentum. Let's consider two objects that are rotating. So imagine that you have two disks that are rotating around the same major axis of rotation. So to make it a little bit easier for you to see this, the axis in the middle is not actually shown on the diagram. So you can imagine that you have sort of have a connection from the outside, and you spin those two disks around exactly the same vertical axis. Now you have a choice. You can spin the disks in the same direction, or you can spin them in the opposite direction. You can spin the disk with exactly the same angular velocities, or you can spin them with different angular velocities. So you have plenty of choices around. And on top of that, you don't have to have the same angular moment of inertia of each of the disks relative to the axis of rotation. And if the moments of inertia are different, that tells you that one of the disks is more massive or has some kind of non-uniform distribution of the mass that is going to make that moment of inertia 3 times larger than the one of the lower disk here. What I'm saying is that this is going to define in a very broad sense a problem that can be tuned in by specifying the initial conditions. Now, if we were to bring the two disks together and make them touch while they're spinning, what can happen to the disks?
You can lose energy.
Okay, fair enough. We might lose energy depending on what.
If friction exists between the point of contact?
Exactly, where the friction exists over there. So if friction existed, that is going to be an external force that is, depends how we are looking at the problem, whether it's a system or individual disks, but can be internal or external forces, right? Another thing could happen is that you bring the two disks together momentarily, and then you separate them, and they're going to start spinning with different velocities, angular velocities, compared to the before the collision, right? So that will be an example where if energy is conserved, that will be an example of perfectly elastic collision in the rotational world. Now, in another imaginary scenario, if you bring the two disks together, and they stick together and they start spinning in the same direction with exactly the same omega, then that would be an example of perfectly inelastic collision, where in the linear world we had two boxes moving toward each other, and after they collided, they actually stuck together and they started moving together as one object after the collision, right? So you can have exactly the same scenarios in the rotational world as the ones we've discussed in the linear world, right? So guys, how are we doing so far? Am I going too fast?
I'm a little bit lost.
Where are you lost?
Like, how could it not spin at the same rate when it's when it touch?
Oh, because you don't sustain the collision for a very long period of time. So I don't have anything that is sturdy and non-breakable in my kitchen here. Otherwise, I would have spun two plates to actually show you this. But what you can do is you can imagine having two plates that are spinning, and you momentarily touch the plates, and then you separate them, right? So that will be equivalent to having two boxes in the linear world that were coming toward each other, they collided, and then immediately after the collision, they're going in the opposite direction. And as long as the energy was conserved during the collision, we call this one an elastic collision. Yes?
So it's like a linear collision and a angular momentum conservation?
No. So let me see what I can spin around. Okay. So I'm going to be spinning the ball here. That will be one object that is rotating. And I'm going to be spinning my concrete here, right? So as long as the two collide while they're spinning, and they collide over a short period of time, and they separate after the collision, and then we define that we didn't lose any energy here, then this collision is actually going to be an elastic collision in the rotational world, right? Otherwise, if we were to have two objects that are spinning around the same axis, but say in a different direction, like I'm spinning the ball here and the hand cream, and then the two objects collide, then can actually start spinning as one object with exactly the same direction and exactly the same angular velocity, right? And during that collision, some of the energy is going to be lost to heat and sound, sparks of light, and so on. And in that particular case, we are going to call this collision a perfectly inelastic collision. Yes? Does this make more sense now?
Yes, thank you.
You're welcome.
Wait, I have a quick question.
Yes.
So if they bump into each other, and there's like, so the friction between the two in that period of time when they like bump into each other, how do we consider that again?
If we consider this as a system, that will be equivalent to the case in the linear motion. You remember that during the collision of the blue and the red particle, back when we discussed linear momentum, right? The collision actually happened because we had action and reaction force between the two particles. And according to Newton's third law, during the collision, those action and reaction forces are internal for the collision. And that means that those forces have to have equal magnitude and opposite in direction. Now, in the rotational world, if you're spinning one plate this way, another plate the other way, and you touch them, there's going to be frictional forces between them. And those frictional forces are going to lie within the same plane of rotation of the plates. Do you agree with that?
Okay, well, yeah, I do, but in linear motion, there's no friction, right? Like in a collision, they just bump into each other and they bump off.
Right, yeah, there is an action-reaction force, but friction here is also an action-reaction force because it happens at the interface between two
Oh, okay. I see what you're saying. Well, okay. So there in linear motion, when we consider friction, it was with the ground, and the ground is always external. But like here,
exactly.
the shit's actually part of the thing, right? Okay, yeah, that makes
So
sense.
if my phone is the lower plate and the box here is the upper plate, and they spin like this, then the interface between them is going to experience the frictional force. But one frictional force applied to the box is going to be applied in the counterclockwise direction, and the one friction that is applied to the phone surface is going to be in the clockwise direction. So the two frictional forces during the collision have to have the same magnitude but opposite direction so they can cancel. Those are internal forces. Yes?
Okay, yeah, that makes sense.
Okay, I'm glad we cleared this one up.
Excuse me, Dita. One last question quickly.
No
So-
problem at all.
You mentioned that they will hit each other at like a very short period of time, correct?
Not necessarily. What I meant to say is that option one, the objects come together closely for a short period of time and then they separate, right? As long as we are not losing energy during the collision here, we are going to call this a perfectly elastic collision in the rotational world. Or the second option, the two objects collide, stick together, right? Energy is lost during the collision, and after the collision, both objects actually start spinning in the same direction with the same magnitude, right? And that would be an example of inelastic collision.
But my question is that you mentioned that if two spinning objects spinning in the opposite direction of each other, right?
Mhm.
They collide and we like pull them apart again. The objects will be spinning counterclock. No, like the opposite direction that it was spinning originally.
Not necessarily. It will depend on the relative moments of inertia and the original velocities. Do you remember in the linear world when we had two objects that were colliding on a straight line, right?
Yes.
Depending on how massive the object was compared to the second one, let's say that this is a fly and this is a truck, right? So when they collide, the fly actually is going to splatter on the windshield, and then afterwards is going to move in the same direction of the truck. And we call this one a perfectly inelastic collision, right?
Okay. I get that. What was it? My question is, say you have like two identical plates that are spinning, right?
Okay.
And you hit them and like you pull them apart. But if energy is conserved, that means that there's no friction. So how would they rotate in the opposite direction?
I didn't say that afterwards they're going to rotate in the opposite direction. I said that this could be an option, and that would depend on the relative moments of inertia and the relative initial velocities. If we imagine a scenario where we have two plates with exactly the same moments of inertia, exactly the same omegas by magnitude, but spinning in the opposite directions, the moment that they collide, if it's a perfectly elastic collision, then what's going to happen is that afterwards, when they separate, they're going to be spinning with exactly the same omega by magnitude. You're not going to have a redistribution of the omega. This is like throwing a ball at the wall, right? And you have a perfectly elastic collision. The ball is going to come back with the same linear velocity that you threw it. I mean, the same speed that you threw it at the wall. Yes?
Oh, okay. I get it now. I get it. It's just a possibility. It's not necessarily true every time.
Exactly. Right. So one optional outcome. Okay. All right. So that took a little bit of while, but it was very important discussion. So I'm really glad that we had it early. Okay. So during the collision, what's going to happen is that we are going to have frictional forces, right, that are going to be acting at the interface between the two objects. And depending on where those forces are located relative to the axis of rotation, they're actually going to introduce torques. Tau 1 for the first object and tau 2 for the second one. So in the linear world, the condition was that the two forces of action and reaction have to be equal in magnitude and opposite in direction. Now, in the rotational world during the collision, the requirement is that the two torques have to be equal in magnitude and opposite in direction during the collision. This acknowledges the fact that those forces can be acting at a distance r away from the axis of rotation. Yes? Does this make sense to everyone?
So there's no situation in which the R's can be different for a given set of forces?
In general, it is possible. I would say that this is going to happen when the objects are not symmetric, right? But with the symmetry that we are given here, that the mass is distributed evenly and the two disks are practically identical except for the masses, then we are going to have the same radial distribution. Now, what we're going to do is we're going to derive the angular momentum conservation law in a very similar way as we did the linear momentum conservation law. So we're going to start with the definition for an angular momentum, which said that L vector is going to equal to moment of inertia times the instantaneous omega. And then we're going to differentiate this equation with respect to time. So then the rate of change of the angular momentum over a collision or an event that takes amount of delta t to happen is going to equal to, what did I do here? Is the formula written on the screen correct?
This should be I, right?
It should be I. So this is how I find out where the students actually pay attention in class. Okay, so we're going to save this one and then we're going to proceed with the lecture. Okay, so the rate of change of the angular momentum is going to equal to the moment of inertia of the object times the rate of change of the angular velocity of the object, right? But then that rate of change of the angular velocity is by definition the angular acceleration of the object, right? And if you remember from the previous lecture, the moment of inertia of the object times the angular acceleration of the object gave us the torque that is applied to the object to make it rotate with that angular acceleration, or the sum of those torques. So now what we have on the left side is change in the angular momentum over a period of time that an event is happening, right? And on the right side, we are going to have the total external torque that is applied to the object or the system in order to change that object's or system's angular momentum. One thing that we can do is we can bring the delta t on the right side of the equation, and then we can examine just the change in the angular momentum. Now, if we do that and we integrate both sides of the equation, right, we're going to find out that the total change in the angular momentum is going to be equal to the final angular momentum after the event happened minus the initial angular momentum. This is before the event. Now, in the special case where there are no external torques that are acting on the system, right, in the direction that we are considering, then what we can say is the angular momentum of an object or a system is going to stay conserved over time. Or the angular momentum of plate 1 before the collision plus the angular momentum of plate 2 before the collision is going to actually equal to the sum of their respective angular momenta immediately after the collision. Right?
Professor?
So, yes?
I don't understand, why are we integrating in this case?
Why are we integrating? Okay. In physics, what we can do is we can do a summation, but the summation is not very precise when you have a function that varies non-linearly over time. So the more precise method to calculate the change is to do actually an integration, right?
We're saying is that the torque that is applied is constantly changing, and that's why we're integrating.
No, what I'm saying is that if the torque varies over time, for example, you push the plates, right, with a little force to begin with and more force, sort of kind of have a spike and then comes back, right? That will be a nonlinear behavior. Do you remember the video that I showed you of a golf ball that was hitting the wall and then reflecting off of it, and the golf ball actually was changing in shape when we talked about the linear momentum conservation? You remember that video, right?
Yes.
Well, the same thing can happen here. The two disks, when they collide, they're not perfectly rigid. So they're going to have some kind of elastic deformation that can occur during the collision. And that happens because the forces that are acting are going to go from 0 before the plates touch to a little bit higher to a maximum, and then they're actually going to start to go down and become 0 again when the two plates separate. Yes, so there's going to be a nonlinear change in the contact forces, and that means non-linear change over time with the torque of contact between the two plates. And because of that, we need to integrate in order to get an exact answer rather than an approximate one. Yes?
Okay, I get it. Thank you.
You're welcome. I know that there is a little bit of negative attitude toward integrals in this class, and I get it. It's something that you haven't studied in your math class, but guys, bear with me. I cannot teach physics properly if I don't mention integrals here. And I'm really trying to kind of use it only when it's absolutely necessary. Okay. All right, so we're going to proceed with the lecture here. One thing to remind you is that when we talked about linear momentum conservation, we identified an isolated system versus an open system. So in the linear world, we said that as long as a system is open to the environment, and that environment can apply any kind of forces onto the system, then those forces have the potential to change the linear momentum of the system. However, as long as the system is isolated and it's close to the environment, then and is subjected only to internal forces, those internal forces cannot change the linear momentum of the system. Now, the same thing actually happens in the rotational world, but the only difference is that instead of forces, we are going to be talking about torques. So as long as the system is isolated, there are no external torques applied from the environment around, then the angular momentum of that system is going to stay conserved over time, or its change is going to come to a total of zero. However, if the system is open to the environment, and that environment can apply external torques to the system, then the sum of all those external torques is actually going to go into changing the angular momentum of the system over the period of time that those torques are applied. Yes?
Sorry, could you repeat that really quick?
Yes. Okay. So let's say that we have a object that is stationary, right? And I push on the object in such a way that I'm going to actually make it rotate. In the beginning, the object was stationary, had zero angular velocity. What was the angular momentum of that object?
Zero.
Zero. My finger pushes on the object and the object starts spinning around with a certain angular velocity. How large is the angular momentum of the object? Is it zero?
No.
It's not. So it's going to be equal to the product of the moment of inertia of this box relative to the axis of rotation times the instantaneous angular velocity of the spinning box, right? So that's how large that angular momentum is. So the angular momentum changed between 0 to a value that is higher than 0. And the way it changes because I applied an external torque to it to make it rotate. Does this make sense now?
I think so, yeah.
Okay. Yeah. Okay. Do you guys have any other questions? Yes.
Yeah, I have a quick question. So you're summing over the external torque, right? So torque is like, so the external torque at one point in time is the instantaneous change in angular momentum, as you say. And then once you sum over all the torques, how is that equal to the instantaneous momentum? I thought the instantaneous change in momentum is the external torque, not the sum of external.
No, it's actually the sum. Let me get another thing here. I'll actually have it. Okay, let's imagine that this cup holder here represents a pulley, a massive pulley, right? That can rotate around an axis of rotation that is at the center of the pulley and perpendicular to the plane of the pulley, right? So it's going to rotate like this. Now, if you imagine that there was a string here and I pull on the string, that means that the force that is applied on the string here, the tension force, is going to have a lever arm relative to the axis of rotation that is going to equal to the radius of the pulley. And that one is going to create a torque due to the tension force. Do you agree with that?
Right.
Okay. Now imagine that at the axis of rotation, because you have sort of like a little rod over there, that rod is going to have an outer surface, and then the hole where the rest of the disc is mounted is going to actually have an internal surface. Imagine that on that contact surface, you actually have friction that is not zero. Yes? Now, if you assume that that frictional force magnitude is constant over time, then we can say that there is a constant torque of friction at the axle of the pulley, right? So now the tensional force here is going to create a positive torque to rotate the pulley this way. But then the frictional torque here is going to actually be acting in the opposite direction. But the angular velocity and the angular acceleration of the pulley is going to be defined by the sum of those two torques. Do you agree with that?
Right, yeah.
Okay, so now imagine the scenario. The pulley was stationary because the system is held in place, right? And then the system is released, an object is falling down, and there is going to be tension on the rope here that is going to make that pulley rotate. Okay, so event one was before we releasing the system. Then we have a moment in time, which is immediately after the system has been released. So then if you look at those two torques, those are external to the pulley. Those two external torques, when you sum them, they're actually going to change the angular momentum of the pulley from 0 to a positive value that's larger than 0. And that change is going to happen over the period of time that those two torques are acting. Yes? Does this make sense? Kind of, did you get the aha moment?
Okay, wait. So the external torque that you're defining is the sum of those individual torques, right? And you're saying that once you sum that external torque as it acts, but isn't the external torque constant over that period?
It doesn't have to be, right? It can be in some occasions, but so the example that I gave you, the frictional torque, we define it as constant over time. I agree. Then the tension, as long as the tension actually stays the same by magnitude, then that torque is going to be constant over time. But it doesn't have to be. There are scenarios, for example, where instead of having a perfectly inelastic rope, you can actually have an elastic one. So that means that the tension force is going to actually be changing in magnitude, and that's going to change over time the tension torque. Yes?
Okay. Okay.
Okay. All right.
Wait, so if you have friction applied at the axle, like how can there be a torque? Because wouldn't that be at the axis of rotation?
No, it's not. It's not kind of a point object, right? So the axle is going to have certain dimensions. Let's say that the black pen here is an axle is going to have an internal radius that we are not ignoring. So there is going to be an outer surface here, and then there is going to be the inner surface of the disc, the large disc that you are applying. So there is going to be, every time you rotate the pulley around the thing here, there is going to be a frictional torque on the surface. Yes?
Okay, so basically we're just dropping some of our assumptions.
Yes. Right. Okay, right. So guys, are you feeling more comfortable right now with the conservation law? Let's say yes or no, or maybe.
Professor?
Yeah.
Isn't this just like similar to like the conservation of linear momentum, but just in the rotation rule?
Exactly the same, and that's why I started with the linear motion here, and then I gave you the rotational motion derivation, and you see it's exactly the same, right? The only thing that is different is the variables that we actually use in the rotational world. And now what I'm going to do, I'm actually going to give you a summary slide. So you have a rotational world here. And then you have on the left side of the slide, and then you have a translational motion in the translational world. So we have the definitions for the kinematic variables, the dynamic variables, like the sum of the torque CQ to I alpha, which is Newton's second law in the rotational world. You have the kinematic equations here. You have the definition for work of a non-constant torque. You have the rotational kinetic energy. I know that we haven't talked about power, so you can skip that one. And then we actually have the angular momentum and the angular momentum conservation law, right? And this is a mirror image of everything that you learned actually in the linear world. So the right part of the slide, most of you, if not all of you, have seen it in high school, already have some idea what's going on. What I'm saying to you is that the rotational world description is pretty much the same. It's just that the name of the variables are different. Yes? Does this make sense?
Yep.
Yeah, I'm not going to ask you for power. It's never going to come on any quizzes and exams because we haven't taught it. So I will be very proper. I'm not going to quiz you on something that we're not studying in class. Okay? So don't worry about this. Okay. All right, so now it's time to actually put all this theory into practice, right? And probably for those of you who have studied angular momentum in high school, your teacher gave you an example with a skater, right? Where the skater actually spins around with the hands that are closed next to the torso, right? And then spins very, very, very fast. And this is because the the moment of inertia of all the parts of the human body, like the arms and the hands and the head and the torso and the legs, they actually come very close to the axis of rotation. So the moment of inertia relative to that distribution of the mass is going to be very small in magnitude. But if the skater wants to stop the spin, one way to do that is that they can actually spread their arms and even spread their legs. By doing that, they're going to change the distribution of the mass to be further away from the axis of rotation. They're going to increase their moment of inertia. And that way, they're actually going to slow down omega, right? Why is it happening? So we have seen it happening on TV when we watch Olympic Games, Olympic skating, but I'm asking you to tell me physically, why is it possible to reduce the speed of spinning by changing the moment of inertia?
Professor?
Yeah.
Well, is it because that angular momentum is conserved? So like, let's say if we increase the value of our moment of inertia, we decrease our angular speed by the same factor.
Exactly, because we define the angular momentum to be the product of I times omega. That is absolutely correct. But I have a follow-up question for you. Are you sure that the angular momentum is conserved in this case?
Assuming it's good ice.
Does it depend on the system?
Right. So if we were considering the skates, for example, they are on ice, right? So if we make the approximation that the friction between the skates and the ice is practically zero, right? Then we can say that the angular momentum of the skater is going to be conserved over time. But what is going to happen if that friction is not zero?
L will be lost. Some of it.
Some of the angular momentum actually is going to get lost, as you say, it's going to change over time. So the question then becomes is, when the skater is spinning, whether the skates actually lie down horizontally on the ice or whether he's spinning kind of on a toe pick, right? If it's a toe pick and there is no, even if there is friction, if we consider the toe pick as one point, that is going to be the point with zero radial displacement relative to the axis of rotation. In that case, friction can be enormous, but because the radial distance is zero, then the torque due to friction is going to be zero and the angular momentum is going to be conserved. However, in reality, that never happens. If you look at the skater here on the left figure, they're spinning. but the edge of the skate is actually lying on the ice and it's moving like this, right? So there is a certain surface that is going to be positioned away from the axis of rotation, and that means that we cannot ignore friction in a real case, and we can only ignore it in theoretical problems that Dida can give you on a quiz or on an exam to make the math a little bit more easier and to avoid integrals. Okay?
And this only happens because the bottom of the shoes are curved.
It's because you have an edge, right? It's not because it's curved. But let's imagine that the edge is like the pen here. So when you start spinning the pen on a surface like this, your axis of rotation is going to be at one end of the pen, right? So that means sorry, somebody was talking? So the rest of the edge is going to have a radial distance relative to the axis of rotation that is not going to be considered zero, right? So that means that if there is a frictional force perpendicular to the edge, then for that particular force, we are going to have a non-zero torque, right? And if the external torque is non-zero, that is going to change the angular momentum. Now, if I ever gave you a problem like the skater here, I'm going to tell you that you should neglect friction to make the calculation very easy, right? And in this case, what's going to happen is that the angular momentum of the skater is going to become zero. And then we are going to have a product of case one, where we have a product of the moment of inertia times omega when the arms are folded. And that one should equal the product of I and omega when the arms are stretched. So when you change the moment of inertia of an object, you're also going to change the angular velocity of the spin of the object. Yes?
If you gave us the constant frictional torque, could we still find the thing?
Yes, absolutely.
Okay.
And you can do that without the necessity of taking an integral, a complicated one. So you're correct. Yeah, I can do that. Because we're going very, very slowly, the next topic that I have on the slide here touches on something very interesting, probably interesting to you because you're engineers. It talks about gyroscopes. Do you guys know what gyroscopes are being used for?
Accelerometers and phones.
Accelerometers in moving objects. What else?
Satellites?
Satellites to actually find out the global position of a system, right? So do you know how a gyroscope works?
Conservation of angular momentum.
It's the angular momentum, and it looks at the change of the angular momentum. So normally I have a very cool demonstration in class, and unfortunately I don't have anything even closely related here at home, so you should actually use your imagination. Now there is a little toy that has this kind of conical shape with a very sharp tip at the end and a little handle at the top, that when you pump the handle, that particular toy called the top is going to start spinning. Have you ever played with a top like this?
Yes.
Yes. Okay. Then you know that when you spin the top really, really fast, initially it's actually standing upright and spinning at very, very high rate. But over time, that top, in addition to spinning around an axis of rotation, is also going to actually start wobbling around. And we're going to see that the axis of rotation is going to start tracing a circle. And over time, that circle is going to go with a wider and wider radius, right? So do we know why this is happening?
Gravity.
I sort of gave you a tip here by showing you the diagram. What, right? So when the top is upright, so work with me. Let's say that this is the top, right? And the top is spinning. When it's perfectly perpendicular to the plane of rotation here, then the gravitational force is going to be applied to the center of mass of the top. And that one is going to be pointing down and is going to be along the axis of rotation. So would that, that gravitational force actually provide a non-zero torque in this case?
No.
Why not?
because torque is the cross product between. Oh, no, it
You're
wouldn't.
correct. You're doing fine.
Yeah, because torque is a cross product between like the radius and the perpendicular, like the
And
tangential
the force, the way that I've actually showed you the equation here, right? So instead of F of force, we're going to actually have an mg. As long as the gravitational force is pointing downward along the axis of rotation when the top is perfectly perpendicular to the table, then that angle here between mg and r is going to be either 0 or 180 degrees. So sine of 0 or 180 is how much?
0.
0, right? So there's going to be 0 torque created by the gravitational force. Now, let's consider another scenario. Let's say that we are just very slightly tilting the top, right? Then what's going to happen is then the gravitational force mg is going to still point downward. But now we have created an angle between that vector force here and the radial distance r that connects the axis of rotation with the center of mass of the top. Now, if we have an angle different than 0, then would the torque be 0 or non-zero?
Non-zero.
Non-zero. And what would be the direction of that force? Torque is going to be outside of the plane where we have the radial vector and the mg. So right now, the radial vector and the mg vector lie in the xz plane here. And that means that the torque vector is going to be actually lying in the xy plane, which is perpendicular to the xz plane. Do you guys see that on the diagram?
Can you show this through like the right-hand rule or something?
Yes, so you're going to have the R and the P, right? So let's say that you have the forefinger to be the R, and the mg is going to be the rest of my fingers here, and then tau is going to be the thumb here. So on the diagram, I have the forefinger pointing this way, and we are going to have the fingers pointing down as an mg, and then the thumb is going to be pointing at the plane that is going to be perpendicular to the xz plane here on the diagram. So that's the orange vector for the torque tau. Yes? Do you guys see that one?
Yep.
Professor, I'm a little bit confused. Why isn't the torque like in the direction of the angular momentum?
Oh, that's a different story over there. We haven't actually, they don't have to be in the same direction. This is an external force that creates an external torque. That torque shouldn't be, in general, in the same direction as the angular momentum of the object. Coincidentally, on occasion, they can be in the same direction, but it's not a requirement. It really depends on the orientation of the external force and the radial distance between the point where that force is applied and the origin of the coordinate system. Yes? And so what happens in a gyroscope like this is that the angular momentum of the top is going to be, as the top is spinning this way, the thumb is going to be pointing at the angular momentum. And now the angular momentum is pointing this way and the torque is pointing this way, right? So then what's going to happen is this torque is going to start changing the angular momentum, right? In a direction that is going to be perpendicular to the plane of the torque. And then what's going to happen is the angular momentum continuously is going to actually change on a part of a circle, where the individual steps of the change delta L are going to be tangential to the surface of the circle. Yeah. So this is going to be the vector diagram for how the delta L is going to be parallel to the torque that is applied, but the torque in general is outside of the plane where the L initial and L final are going to lie. The only thing that we have is that the DL or the delta L is going to be parallel to the external torque tau. And then how this is going to translate to the top is that we have the initial angular momentum R initial. we are going to create this change in the angular momentum delta L that is going to be tangential to the circle of this cone along which the angular momentum is going to be spinning. And then the final momentum is going to be the vector that is going to be the sum of L initial plus the delta L change that we have. Does this make more sense?
Professor?
Yeah.
So is the L initial in the XZ plane?
The delta L is going to be in a plane parallel to the rotational plane.
No, but the L initial, is that in the XZ plane or?
Yes, we can imagine that the L initial is going to be in the XZ plane, right? Then when we apply the delta L, which is going to be perpendicular to that plane because it's in the same direction as the torque tau, then that's going to change the L final to be outside of this XZ plane, right?
I see, thank you.
You're welcome. Okay, all right. So enough of gyroscopes. I wish I could spend more time, but we are almost out of time. And I want to solve at least one problem to showcase the angular momentum acceleration. Oh, if you're interested in gyroscopes, here I provided 3 different YouTube links. Very cool movies over there. I think you're going to like them. As engineers, I assume that you're going to like them. Okay. So this is a particular problem that we have given both in quizzes in the past and in a past final exam. So I want to showcase to you basically what kind of level of difficulty you should expect from an angular momentum conservation problem. Right. So the scenario is following. We have a solid cylinder which is rotating around a fixed axis of rotation at point O, oriented along the long axis of the cylinder. Now, the mass of the cylinder is distributed very evenly and homogeneously within the volume of the cylinder. And originally, the cylinder is completely stationary. We know the total mass of the cylinder, and we know the radius of the cylinder here. Now, at one point, we throw a little piece of mud or Play-Doh, right, in the form of a little ball. We know the mass of the ball, and we know the instantaneous velocity, linear velocity of the ball immediately before it touches the surface of the disc, of the cylinder here. The other thing that we know is the height of the contact point relative to the dashed line here that passes through the center of mass of the cylinder here. So we have this kind of height adjustment of where the collision is going to happen. Right. Now, what we are asking to find out in this case is what would be the angular speed of the system once the little ball of mud actually sticks to the surface of the cylinder, right? And the second thing we'd like to find out is how much mechanical energy is going to be lost during the collision. So the second question sort of tells you the type of the collision, yes? Is it going to be elastic or inelastic?
Inelastic.
Perfectly
Yes.
inelastic.
2 tips there, because the 2 objects are going to stick together after the collision. And second, we're being asked to find out how much energy is lost. So we know that we're dealing with inelastic collision here. Okay, so the little ball is going to have a linear momentum before the collision. Does the cylinder have any linear or angular momentum before the collision?
No.
No,
Separate.
excellent.
No.
Now, immediately after the collision, the little ball is going to stick on the circumference of the cylinder, and both of them are going to spin at the same omega. Now, which way they're going to spin? Are they going to spin clockwise or counterclockwise?
Clockwise.
Clockwise.
Clockwise. Okay. Now, what we've done so far, that was the conceptual analysis. Right now, we need to actually start putting things into numbers. Okay. Because this is a collision, right? Do we expect the angular momentum of the system, little ball, and the cylinder to change over time?
Yes.
Okay, why?
My bad. No.
So you changed your answer, but can you explain why?
Yes. So when so when they would collide, since there's no external additional forces, then the total combined linear and rotational momentum of both would be conserved. It would just be changed from one type to another, I guess.
Okay, so I will accept this answer as correct, but with one minor correction here, right? Is it true that no other forces in the universe are actually acting on the system during the collision? What about gravity?
Can we
Is
factor
gravity
that
going
out?
to- what?
Can we factor that out since it's like since it has the same effect and it's like perpendicular to the plane of initial
So gravity
motion?
is going to be pointing downward, right? The motion of the particle happens in this direction, including the spin, right? So then what's going to happen is that the effect of gravity is actually be constant over time. So there is not going to be a change in the torque due to gravity before the event and after the event, like before the collision versus after the collision. Only if we see a change in that that effect, at that torque, then we can actually talk about the effect that it might have. So in this case, gravity is not going to change the angular momentum of the system little ball with the cylinder here. Okay, so if that's the case, then the angular momentum of the system is going to be conserved over time. So we can say that the delta L for the entire system is going to come to a 0, which means that L of the system before the collision should equal L of the system after the collision. Now notice that the little ball has a linear momentum. The cylinder, because the only option for the cylinder is to spin around the axis, it only can have an angular momentum. So right now we have an apple and an orange to work, because apple is in the translational world and the orange is in the rotational world. So which conservation law should we be using? The linear momentum conservation or the angular momentum conservation?
Can't you convert like the linear momentum of the small ball into like an angular momentum with respect to the origin of the axis on the cylinder?
So you're saying with respect to point O here, yes?
Yes.
Excellent. That's an excellent suggestion, right? Guys, a tip. Whenever you actually have two objects in the system and one can only spin and the other one can translate but can also spin if it wants to, right? It has the possibility to do both. Then always actually solve the problem in the rotational world, because if one object is restricted only to rotation, like the cylinder, it cannot translate, then we have to pick the world where it's going to describe its motion, right? So in this case, we are dealing with an angular momentum, and whoever your colleague was that suggested that we calculate the angular momentum of the point mass relative to O was absolutely correct. Okay, so that's exactly what we're going to do. Now, how we're going to do this, that's a different story. Okay, so what we're going to do is we are going to extend a dashed line from the axis of rotation, the point O, to the point of contact where the little ball actually is going to get stuck on the surface of the cylinder. And we are going to make this in the same plane. If we cut the cylinder, we are going to do this along the same disk, right? So then what we're going to do is we are going to translate the red vector in the forward direction here, and we are going to extend the radial vector in the upper direction here. And then what is going to happen is that we are going to find out that the cross product between the two of them is going to equal to MVR sine of the angle phi, right? Do you see how we got this one, or do you want me to write it down explicitly?
Could you write it down?
Yes, I can. It's going to take me just a little bit of time to do that because I need to put intermediate slides. Okay. All right, so that's going to be review. Can you still see the slide, the blank one?
Yeah.
Yes.
Okay. All right, so we are going to have the cylinder here, like this. It's not a perfect circle, right? And the little ball that is coming in is going to be coming in this direction, and it's actually going to get stuck in this position here. So this is going to be the radial vector r. And then that ball is going to actually have a linear velocity or linear momentum. We are going to call it P here. And you see how I extended the vector from the point of contact in the direction of the motion. Now, what I'm going to do is this vector, the radial one, I'm actually going to extend it like this. And I'm going to translate it in this direction here, like this. So that one is going to be the radial vector like that, okay? And I'm just going to erase this part here because it's going to get in the way. Okay, so one other thing that I want to kind of erase, I want to make this one dashed line, like this. Okay, are you with me so far? Guys? Yes or no?
Yeah, I'm
Really
with
quick.
you.
Okay,
Okay,
so
yeah, continue.
this is the angle phi. And then because this line is parallel to that one, this is going to be the angle phi. And then this big angle here between R and P is going to be how much? This angle here?
Pi
180 minus 5.
Pi minus phi. Okay, so right now, the angular momentum of the little ball with respect to point O, oh, actually, I'm writing it the wrong way. Okay, so the angular momentum of the little ball here with respect to point O, right, is going to equal to the radial distance r cross the linear momentum of the particle. That was by definition, correct? Now, this one is going to translate to the following. Is going to have the little ball with respect to O by magnitude is going to equal to the magnitude of R, magnitude of P, and then sine of the angle between those two vectors, which is going to be pi minus phi. Are you with me?
Can we just say the sign of phi?
Excuse me?
Can we just say the sign of phi because they will be equal?
I'm being really proper right now by walking you through every single step very in great detail, right? If you tell me the sine of pi minus phi is equal to sine of phi, I absolutely agree with you. That's exactly what we're going to write here, that this is going to equal to sine of phi, right? Okay, now this thing here is equal to mv. And that's the initial velocity of the little particle. So then our final, our final expression for the angular momentum of the little particle relative to point O by magnitude is going to be mv initial, and then is going to have an r sine of the angle phi. Now, let's consider that we are given this distance d here. Is the value of d related to the radius and the angle phi?
Yes.
How?
D over radius would be the sine of phi.
G over the radius. Okay, yeah, that's correct. Or you're saying that r sine phi is going to equal to d. Is that correct?
Yes.
Okay, so then as a final answer, we are going to say that L of the little particle with respect to point O by magnitude is going to equal to m v initial times d. Like this one. It makes more sense? Do you want me to keep the slide in the slideshow when I post the presentation?
Yes, please.
Okay.
Why is it equal to D?
Excuse me?
Why is R sine phi equal to D?
Okay, so let's have a look at this triangle here. I'm just going to erase a few things to make it a little bit easier for you to see. So this is the radial vector R. Do you agree with that? This is the angle phi here. And then if you were to put the vertical line here, that is going to be D. Now you see it?
Yes, thank you.
You're welcome. Okay, so now we're actually going to save this one. And we're going to come back to this slide. All right. So then on the left side, we actually have the angular momentum of the system before the collision, which happens to be only the angular momentum of the little ball because the cylinder was not spinning. But afterwards, the cylinder plus the little ball, so that's B is for the ball and C is for the cylinder, they're both going to spin around an axis of rotation at point O with a certain moment of inertia and with a certain omega final, right? So now, in order to find omega final from here, we need to divide this expression here by the moment of inertia. Now, the moment of inertia has additive properties. So basically what we can say is we can take the moment of inertia of the little ball and consider that one a point mass. So it's going to have an mr squared moment of inertia. And then for the cylinder, we know that it has 1/2 m capital R squared, right? And instead of the R sine phi here, we're actually going to put the D parameter that we got. So we're going to have MVI initial D. So then, if we rearrange the parameters a little bit and cancel a few things, we're going to happen to find out the final expression for omega final, right? Does this make sense? Oh, I missed the chat. Okay.
Wait, so with R, we're basically treating the initial moment as like right before the impact.
Well, this is afterwards. So when the ball gets stuck here at the surface, is at the circumference of the surface of the cylinder, which is 1 radius away. But for a point mass, if you remember, we defined the moment of inertia of an mr squared, right? Where r is the radial distance relative to the axis of rotation. So mr squared here is going to be the moment of inertia of the little mud ball. And then the 1/2 of m capital R squared is going to be the one for the cylinder, which is equivalent for a solid disk. Yes?
Gotcha. Yeah.
Okay. So how do we find out how much energy is lost during the collision?
The change in kinetic energy.
Okay, so we're going to look at the change of the kinetic energy of the system from before the collision and to the after the collision. Is that what you're saying?
Yes.
Excellent. Okay, so I'm going to follow your advice. So we're going to define as E lost, energy lost, is equal to the change of the total energy of the system, right? And because we don't have any gravitational potential energy or springs or anything else, then that is going to be the rotational and the translational energy of the system in the final case, minus the rotational and the translational energy of the system in the initial case. Now, the reason why I'm actually putting rotational and translational energy, because in the beginning, the mud ball is just translating, is not spinning. But afterwards, the disk and the ball are spinning around, right? So in one case, we're going to have translational energy, in the other one, we're going to have rotational one. So in this equation here, the final translational energy is going to be 0, and the initial rotational energy is going to be 0. So those ones are going to go away. And what we're going to be left is going to be the rotational kinetic energy when the ball is stuck on the surface of the cylinder, right? Minus the initial kinetic energy of the ball as it was flying toward the cylinder immediately before the collision. And then what we can do is we can rearrange the parameters. And if we take the expression for omega final here from equation number 3, and we plug it in, we can simplify the expression for the lost energy and express it only in parameters that were actually given in the text of the problem. Yes? Do you guys have any questions? Right. Shall I assume that there are no questions? Oh, no questions. Okay. How do you feel about this problem? Is it difficult or is it okay now that we've seen how the solution actually can happen?
It's okay.
Okay. All right, great. So now we have the following two options. As I promised you, I can stay for about half an hour to answer any additional questions any of you have. You don't have to stay for that additional time. If you have other things to do, you're welcome to sort of leave the lecture room. If you do have questions, I'm happy to stay for a little while and talk to you about physics. Right.
Could I ask a question?
Sure, go ahead.
It's kind of at the back when you were saying like T1, torque 1 is equal to negative torque 2. I kind of missed that. So if you could explain that again, that would be great.
Yeah, I can do that. Just give me a second because my computer kind of got stuck a little bit here. Okay, so we talked about the angular momentum conservation, right? So in the linear world, when we had two objects moving on a straight line and colliding, we had contact forces, like one bumps into the other, but the second one bumps into the first one, right? So if one of them is pushing the second one pushes back, right? When we have rotational plates, like the one that are shown here, if one is spinning one way, the other one is spinning the other way, the moment they touch, there's going to be a contact between them. So that contact forces, in this case, are going to be frictional contact forces, right? Because those are going to oppose the motion, the rotational motion of each of the object within the plane of the rotation, right? Now, depending on where those forces are located along the radial direction, they can have a certain torque associated with them, right? So in the rotational world, we don't talk about forces, we talk about torques, because we always have to consider the point where that force is applied relative to the axis of rotation, right? And again, as long as those two torques are contact torques, right, happening within the collision of two objects that are spinning, then according to Newton's second law for the rotational world, those two contact torques have to be equal in magnitude and opposite in direction, right? So they cannot change the angular momentum of the system. They're going to cancel each other. Yes?
Yes.
Okay.
Yeah.
Did I answer your question?
Yes.
Okay, great. Does anybody have any other questions? No? Very quiet?
Oh,
So
someone wrote it in the chat. Sorry.
Oh, right. Sorry. I forgot to check the chat. How did we get equation 2 on which slide? Ethan? So on which slide? Okay, maybe he left. Okay, so I don't see any other questions here on the board. Okay. All right. Does anybody else have a question? Voice it out or type it.
Professor?
Yeah.
For the last question that we did, could you go back to it?
Yes, I can. Right, this one.
Yeah, so for the moment of inertia for B and C, how did you get the mass to be m/2 plus m for the fourth equation?
This one. Okay, so here, I'm not sure what I did here. Okay, so the 1/2 comes from the energy. That's the one outside, right? The second half comes from the fact that we have a 1/2 here for the cylinder. Yes?
Yep.
So my calculation here is correct, yes?
Oh, okay. I get it now.
Okay. All right. Any other questions? Okay.
Could you go back to the slide with the skater for a second?
Yes.
I just want to look at it.
I'm going to post the slides in a little bit. Just give me maybe about 15 minutes so I can kind of remove the additional slides that we haven't gone through and put them in this file for tomorrow.
So could you just briefly explain again how the change in, what is that, angular momentum is parallel to the torque? Is that true?
Yes, yes, absolutely. So that comes from this equation here, right? So the net torque, right, which can be a single torque, is going to equal to dl dt. Now, the dt is a scalar variable. You can imagine it like being a constant, right? So because the angular momentum is a vector here, then that vector is going to have a certain orientation. And that means that the torque, which is equal to dl divided by a constant, is going to have exactly the same orientation as dl.
Yeah, and that came from deriving the
angular momentum conservation here. Yeah, you remember this?
yeah.
Here?
It came
right?
from there. Okay.
So the delta L over delta T is going to equal to the external torque here, or the sum of the external torques. The delta T is going to be a constant, right? It's not going to vary over time at this time period here. And then that means that the direction of the delta L is going to be determined by the direction of the external force, external torque. So then when you go to the gyroscope here, you find out that the direction of the torque is applied in the XY plane, right? While the product of mg and r is in the xz plane, right? So if the L vector was here initially in the LZ plane, right? Then that delta L here is going to have exactly the same orientation as the torque here. So this diagram is written, actually is prepared brilliantly to actually showcase that case here. Yes?
Okay, so while it spins around, the change in angular momentum is related to the torque that is applied to the system.
Yes.
And that explains the motion of this spinning object.
Exactly,
Okay.
because then you have the initial angular momentum, and then you add a little change to it, and then you end up with another angular momentum vector. Yes, and that angular momentum is just going to be transposed in 3 dimensions in such a way that is actually going to lie along the surface of this kind of conical shape. Yes?
Yeah. Okay. Thank you.
You're welcome. Okay, guys, if you don't have any other questions, shall we call it a night? Okay. We're going to stop sharing here, and I'm going to say goodbye.
Thank you.
You're very welcome. Since this is a new topic, I suggest you review it tonight, because tomorrow we're going to be solving more problems from it. And it will make it easier for you if you can review this in advance. Okay, bye-bye.